the 5 threats to internal validity that we have discussed, they concern the first OLS assumption, which is that the residuals, the expectation of the residuals, is equal to 0 no matter which level of x we look at. So these might, in some cases, lead to biased and inconsistent OLS estimates. But now we are going to look at violations of the second OLS assumption, which is that the observations of x and y are independently and identically distributed. So violations of this assumption do not lead to biased and inconsistent OLS estimates. However, it is a problem for the standard errors. So it does lead to inconsistent standard errors. So what is the result of that? It's that the hypothesis test that we do not have the significance level, and the confidence intervals do not have the desired confidence level that we initially would like from our study. So what does it mean when a hypothesis test does not have the desired significance level? So the significance level is, which we often call alpha, is the tolerance for a type 1 error. Okay, so often we have a set of data, right? And our H naught is that of beta 1 equals 0, right? That the slope is 0, which means that y has no effect on x does not have any related effect on y. Okay, if we have a beta different from 0, for example this beta 1 different from 0, then that would be our alternative hypothesis. Just beware that we can have any beta different from 0. It doesn't need to be positive as in this case. So for example, this is our H naught, and this is our alternative hypothesis. Okay, so if we conduct a hypothesis test with a significance level equals 0.05, this means that in 5% of the cases, in 5% of our analysis, we would expect that even if the true beta actually is 0, then we reject the null hypothesis of beta equals 0, for example, and adopt a beta, the alternative hypothesis of beta different from 0. Okay, so and if this hypothesis test in which we believe or of which we believe has a probability of a type 1 error does not have a probability of a type 1 error equal to what we believe, equal to 5%, then we are led to kind of reject or not reject H naught based on a different probability than we assumed for our analysis. Okay, so and equivalently, if we look at the confidence interval, so this is, for example, the real number line, and this is our beta hat of our slope, then we create a confidence interval. If we assume the normal distribution, we have a lot of data, then we go plus 1.95 standard errors to the right, and negative 1.96 standard errors to the left, to the downside, and we say that this should be 95% of in 95% of the cases, we should actually capture the true beta in this range. Okay, so and if we repeat the analysis, then in 95% of the cases, we should be able to capture the true beta 1. Okay, so you can show this like this. Analysis number 1 has a confidence interval in this range, right? And this is the number line, and for example, the true beta 1 is here, then we expect the second analysis to have a 95% confidence interval, and the third one and the fourth one, and maybe they have maybe the fourth one misses, but 95% of your analysis will have a confidence interval which actually includes the value of the true beta. But if because of heteroscedasticity, that we do not have the correct standard errors, then we are led to believe that we have a 95% confidence interval, whereas the true interval should have been larger. So we might end up believing that we have a certain estimate, whereas the truth is that we do not have a certain estimate. The estimate should be wider, for example. So that's the effect of heteroscedastic error terms on the beta estimates.